So let's look at Euler's theorem. It states that if G is a planar graph, the number of vertices minus the number of edges plus the number of faces equals 2. This is not an if and only if statement. Part of the reason is because the concept of faces doesn't make sense if you don't have a planar graph. So it's not even a well-defined statement if the graph's not planar. Okay, so it doesn't give us a perfect characterization of planar graphs, but we'll see that a necessary condition is often pretty good for determining when a graph isn't planar. But let's prove this theorem. So how are we going to do the proof? Well, one of the best methods of proof is induction. Induction on what? So there are lots of things we could induct on: the number of vertices, the number of edges, or the number of faces. It turns out that in this case, we want to do induction on E. Okay, so our base case is going to be E equal 1. Okay, so we're taking a graph with one edge. There are two possibilities for a graph with one edge. One possibility is that we have this edge, and another possibility is that we have a loop. Nobody said the graph had to be simple. So now we want to just check that in both of these two base cases, Euler's theorem holds. Here, I've got two vertices, I've got one edge, and I've got one face. The whole thing's a face. Yep, that equals 2, so I'm good. Here, I've got one vertex, one edge, and now I have two faces, the inside and the outside. So plus 2, yep, that works. And they work for different reasons, which is kind of interesting. So, all right, Euler's theorem is true in the base case. We're doing induction on the number of edges. Okay, so now I get to assume that G has more than one edge. So assume G has E greater than 1 edges. Now we get to know that the result is true for any graph with fewer edges. So the inductive hypothesis says that it's true, Euler's theorem is true, if G prime has less than E edges. So the idea is we want to reduce the number of edges. We're going to do it in two cases. Okay, so case one, G is a tree. Let's think about this case. Let's turn this guy into a tree. Okay, now we have a tree. So how can we think about this in terms of a tree? Well, actually, I don't even think I need induction on this one. I think I can just do this one. So I know the number of edges on a tree is one fewer than the number of vertices. So if G is a tree, I know that E is equal to V minus 1. I also know that a tree has no cycles, so there's no inside for any face. So a tree also has one face. So what do I get? I get V minus the number of edges, which is V minus 1, plus the number of faces. What's that? Well, that's 2. Okay, done. I didn't even need induction for that. Okay, great. So I've done it for trees. And sometimes that's a good place to start. Trees or bipartite graphs are often a good place to start working out cases to get intuition. So case 2, let's just say G is not a tree. So let's assume that G has a cycle. That's what it means for G not to be a tree. So let's take our tree and turn it back into a generic graph. Now this graph has a cycle. Now how can I think about this case? Well, I want to think about how I could remove an edge. That's going to allow me to use my inductive hypothesis. If I can remove an edge and then conclude something. So I've got my graph here. This is my graph G. What if I remove this edge? It's the edge in a cycle. If I remove this edge, my graph stays connected. Now what's happened? My number of vertices has stayed the same. The number of edges has dropped by 1. What's happened to the number of faces? So I haven't changed the vertices. I've lost one edge. What's happened to the faces? Well, I had this face and this face, right? The inside and the outside for this edge. Removing this edge consolidated them, so I lost one face. So the number of edges went down by 1, and the number of faces went down by 1, so the Euler characteristic stayed exactly the same. So I've written the notes down in the notes, the details of that proof, but it's really good one just to visualize. The key to the proof is we're doing induction on the number of edges. So you want to take an edge away. And all we have to do is think about what happens to each of these 3 pieces of the puzzle. So taking this edge away keeps my graph connected. That's important. And it's all, sorry, this does need to have a connectedness assumption. So pretend I said that in the beginning. So we would take this edge away. We've lost a face, lost an edge, kept the same number of vertices. Therefore, by induction, the smaller graph satisfies Euler's equation. So the larger graph, by the fact that 1 minus 1 is 0, also does.